The sky is very slightly warmer in one direction than the other, about 3/1000ths of a degree toward the constellation Leo, and 3/1000ths cooler behind you toward Aquarius. That tiny difference is the only measurement anyone has ever made that answers the question of how fast you are actually moving, not relative to the ground or to the sun or to anything you could point at. Actually, tonight we added up one layer at a time. The spin under your feet, the orbit you inherited, the star you are riding, the arm of the galaxy you are drifting through, and the lap that takes 230 million years. Each one real, each one unfelt, and none of them the last. If you would rather listen with the screen dark, this channel is on Spotify too, and the link is in the description. Tell me in the comments where you are listening from and what the clock says. Now slowly, let yourself settle. Nothing tonight requires any effort from you. I want to say a word about the shape of this one because it is a stacking rather than a story. We are going to add layers. Each layer is a real motion you are performing at this moment, and each one is larger and slower than the one before it, and by the end, there will be 6 of them running at once inside one another like a set of nested wheels. And then at the very end, we will ask the question that has been sitting underneath the whole thing, which is the one children ask and physicists spent 300 years failing to answer. Moving relative to what? There is a real answer to that, and it was found in 1977, and it is written on the sky in a temperature difference so small that you would need an instrument cooled with liquid helium to read it. But we will get there slowly. If you fall asleep somewhere around the 3rd or 4th layer, the rest will still be true, and you will still be doing all of it. Let's start with the strangest part, which is not any of the speeds. It is the fact that you cannot feel a single one of them. Consider what your body actually detects. You have a balance system in your inner ear, and it is genuinely good. 3 fluid-filled canals, arranged at right angles, each with a little jelly-covered bundle of hair cells, and when your head rotates, the fluid lags behind and bends those hairs, and you know you have turned. Alongside them sit 2 more organs, where tiny crystals of calcium carbonate rest on a membrane, and when you accelerate in a straight line, the crystals lag and drag the membrane and you feel the push. That system is sensitive. It can detect accelerations well below what you would notice consciously. But look at what it detects. Rotation and acceleration, changes in motion. It has no way whatsoever to detect motion itself. Sit still in a stationary train and watch the train on the next platform begin to move. And for a moment you are certain you are the one moving. Your eyes voted and your ears had nothing to contribute because there was nothing for them to contribute. A body moving smoothly at constant speed produces no signal in any sense organ you have. This is not a shortcoming of biology. It is a fact about the universe, and it was written down 400 years ago in a passage that is one of the most beautiful things in the history of physics. In 1632, Galileo Galilei published his dialogue concerning the 2 chief world systems, arranged as a conversation between 3 characters over 4 days. In it, he addresses the strongest objection to the earth moving, which was not religious but physical and entirely reasonable. If the earth were hurtling through space, surely we would feel it. Birds would be swept away. A dropped stone would land behind you. The whole world would notice. Galileo's reply is to invite you below decks Shut yourself, he writes, in the largest cabin below deck, on a large ship, with some flies and butterflies, a bowl of water with fish in it, and a bottle hung up dripping into a vessel beneath. Watch carefully how the flies move about the cabin in all directions equally, how the fish swim without favoring any side, how the drops fall straight into the vessel below. Now have the ship move as fast as you like, provided the motion is steady and not rocking. You will not be able to tell the difference, not by any experiment. The flies still fly in every direction. The fish still swim without effort toward the back. The drops still fall straight down. If you jump, you land where you took off, and you can jump just as far toward the stern as toward the bow, even though the ship has slid many meters beneath you while you were in the air. Everything in the cabin shares the ship's motion, so there is nothing left to measure the motion against. This is now called Galilean relativity, and it is the founding principle of all of mechanics. There is no experiment you can perform inside a smoothly moving system that will reveal that it is moving, which is precisely why you have never felt the speeds we are about to discuss, and never will. And notice the word steady. It matters. If the ship rocks or turns, or the engines change note, you feel it instantly. Acceleration is detectable, steady motion is not. Everything we count tonight is very nearly steady on any time scale a body could notice. The turns are so gentle that the acceleration involved is thousands of times below your threshold. So the motions are invisible not because they are small, but because they are smooth. And it is worth pausing on how long it took to establish even the first two layers, because the resistance was not stupidity. Around 270 before the Common Era, a Greek astronomer named Aristarchus of Samos proposed that the Earth goes round the sun rather than the other way about, and that the Earth turns daily on its own axis. His own writing on it is lost, and we know of it mainly through a passing reference by Archimedes. The idea was rejected, and the objection was empirical and entirely sound. If the Earth moves around a large orbit, then nearby stars should shift against the more distant ones as we view them from opposite ends of that orbit. Parallax. Nobody could see any. There were only two explanations. Either the Earth does not move, or the stars are so unimaginably far away that the shift is too small to detect. And the second seemed absurd, because it would make the universe vastly larger and emptier than anyone was prepared to believe. They chose the answer that kept the universe a reasonable size. Given what they could measure, that was the responsible choice. The same objection was still live nearly 2,000 years later, when Tycho Brahe, the finest naked-eye observer who ever lived, considered the Copernican system in the late 16th century. He could not find parallax either, and he had the best instruments in Europe. He proposed a compromise instead, with the planets going round the sun and the whole arrangement going round a stationary Earth. And there was a second objection which we met at the start of tonight. If the Earth is moving, why do we not feel it? Why are we not left behind when we jump? Galileo's cabin answered that one in 1632. Bradley's aberration answered the first one in 1729 by demonstrating the motion in a way parallax had failed to. But actual parallax, the thing Aristarchus was condemned for lacking, was not measured until 1838 when Friedrich Bessel finally caught it for a star called 61 Cygni. He got a shift of about a third of an arcsecond, which is roughly the angle subtended by a small coin at a distance of 10 kilometers. The distance came out at around 11 light years, and the ancient objectors turned out to have been wrong about the correct answer for exactly the right reason. The stars are unimaginably far away. The universe is vastly larger and emptier than anyone was prepared to believe. It took 2,100 years to settle a question about whether the ground under your feet is moving, which is a reasonable measure of how well hidden all of tonight's motions are. Right? Layer 1, you are spinning. The Earth rotates once on its axis approximately every 23 hours, 56 minutes, and 4 seconds. Not 24 hours, that is the solar day, the time for the sun to return to the same place in your sky. And it is a few minutes longer because the Earth has also moved along its orbit during the rotation and has to turn slightly further to catch up. The true rotation, measured against the distant stars, is the sidereal day, and it is about 4 minutes short of the day you live by. How fast that carries you depends entirely on where you are. At the equator, the Earth's circumference is a little over 40,000 kilometers, and you go round it in a day, which works out at about 1,670 kilometers per hour, around 460 meters every second. At the latitude of London or Amsterdam, it drops to about 1,000 kilometers an hour. At the latitude of Anchorage, closer to 700. And if you were standing exactly at the North Pole, you would be turning on the spot once a day and going nowhere at all. You could take one slow step around the pole and cross every line of longitude on Earth. This is why rockets launch eastward and why launch sites cluster near the equator wherever politics allows it. Cape Canaveral, Kourou in French Guiana at 5 degrees north, Sriharikota in India. A rocket lifting off is already moving east at several hundred meters per second before it has done anything, and that is free speed toward orbit. Now, the fact that this was ever in doubt is worth sitting with because, for most of history, the spinning Earth was not obvious. It was a scandalous claim with no direct evidence. Everyone knew the sky appeared to turn. The question was whether the sky was turning or you were, and from inside, as Galileo's cabin shows, those two look identical. Copernicus made the argument in 1543 on grounds of simplicity. Galileo argued it. Newton's physics required it. But nobody had ever pointed at anything and said, look, there it is, the Earth turning. That happened in 1851, and it happened in Paris, and it was done by a man with no formal scientific training. Léon Foucault had studied medicine and abandoned it because he could not stand the sight of blood. He worked as an experimenter, was a gifted instrument builder, and had a habit of finding demonstrations that other people had missed. His idea was a pendulum, and it is beautiful because it needs no equipment at all beyond a heavy weight and a long wire. A swinging pendulum keeps swinging in the same plane. There is nothing to turn it. Gravity pulls straight down, and the wire pulls along its length, and neither of those can twist the swing sideways. So if you hang a pendulum and set it swinging, and the plane of its swing appears to rotate slowly over hours, then it is not the pendulum that turned. It is the room. He first demonstrated it in his own cellar, then at the Paris Observatory, and then in February and March of 1851 in the Pantheon in Paris, with a 28-kilogram brass-coated bob on a wire 67 meters long hanging from the center of the dome. Crowds came. The bob swung slowly back and forth, taking about 16 seconds for a full period, and it carried a stylus that traced a line in sand, spread on the floor beneath, and the line moved slowly, steadily, about 11 degrees an hour at that latitude, always clockwise in the northern hemisphere. There was nothing to argue with. You could stand there and watch the planet turn under your feet in an afternoon. The rate depends on latitude, which is itself elegant. A Foucault pendulum at the pole would complete a full circle in one sidereal day, and at the equator, it would not rotate at all, and everywhere in between it goes at the sine of your latitude. There are Foucault pendulums in museums all over the world tonight, quietly swinging, quietly demonstrating the same thing. The spin has other fingerprints too, once you know to look. Anything moving freely across the surface of a rotating sphere appears to curve. This is the Coriolis effect, described mathematically by Gaspard Gustave de Coriolis in 1835 in a paper about rotating machinery, and it is why weather systems spiral counterclockwise around a low-pressure area in the northern hemisphere, clockwise in the southern. It is not, and I want to be firm about this because it is one of the most persistent pieces of misinformation in circulation. The reason water spirals down a drain in a particular direction. The Coriolis effect at the scale of a sink is absurdly weak, thousands of times weaker than the influence of the shape of the basin, how the water was poured in, and any residual swirl. Storms are large enough and long-lived enough for it to accumulate. A bathtub is not. The spin also shapes the planet. Earth is not a sphere. It bulges at the equator by about 21 kilometers because the material there is being flung outward slightly, which means the summit of Chimborazo in Ecuador, sitting almost on the equator, is further from the center of the Earth than the summit of Everest, despite being over 2,000 meters shorter above sea level, and it means you weigh slightly less at the equator than at the poles, about 0.5%, partly the bulge, partly the rotation. That is layer 1, 460 meters a second at the equator, unfelt, and it took until 1851 to see it directly, and before we leave the Earth entirely. There are two smaller motions of this planet that are worth a moment, because they run on timescales that bracket a human life on either side. The first is fast, and you can watch it happen. The Earth and the Moon do not orbit each other in the way the diagrams suggest, with the Moon circling a stationary Earth. They both orbit their common center of mass, and because the Earth is about 81 times more massive, that point lies inside the Earth, roughly 4,700 kilometers from the center, which is about 3/4 of the way out toward the surface. So the Earth is not sitting still while the Moon goes round. It is describing its own small monthly circle around that point, wobbling as it goes, which means that on top of everything else tonight, you are also being swung in a circle roughly a month long at something like 12 meters per second. And the same relationship produces the tides, which is a motion of the surface itself. Twice a day, the ocean rises and falls, and in some places, like the Bay of Fundy in Canada, the range exceeds 15 meters. The whole solid body of the Earth flexes too by something like 30 centimeters, though you have no way to notice because everything around you rises and falls with it. The second motion is slow enough that it took the ancient world centuries to detect. The Earth's axis is tilted by about 23.5 degrees, which is what gives us seasons. And that tilted axis is not fixed in direction. It is slowly sweeping out a cone like a spinning top, wobbling as it slows, taking about 25,700 years to complete one circuit. It is caused by the sun and moon pulling on the Earth's equatorial bulge, trying to tug the tilt upright, and the spin converting that pull into a slow, sideways swing. It has a name, and it was found around 130 before the Common Era by Hipparchus of Nicaea, who compared his own careful measurements of star positions against records from Babylonian observers a century and a half earlier, and noticed a systematic drift. The whole sky had shifted slightly relative to the seasons. It is called the precession of the equinoxes, and it has two consequences you can point at. The first is that the pole star changes. Polaris happens to sit near the northern celestial pole now, which is convenient, and it is a recent arrangement. Around 5,000 years ago, when the pyramids at Giza were built, the pole star was Thuban in Draco. In around 12,000 years, it will be Vega, which is one of the brightest stars in the sky and will make an unusually good one. The second is that the astrological signs no longer match the constellations they are named after. The zodiac was fixed relative to the seasons more than 2,000 years ago, and the sky has drifted by roughly a whole sign since. When a newspaper says the sun is in Aries, the sun is in fact in front of Pisces, so even the axis you are turning around is turning. Layer 2 is larger by a factor of 60. This planet is in orbit around the sun, and it travels along that orbit at approximately 29.8 kilometers per second. We have talked about this number on this channel before, but tonight it is one layer among several. So let me put it in the body rather than in the abstract. 29.8 kilometers every second is around 107,000 kilometers per hour. In the time it takes you to breathe in comfortably and slowly, you have traveled about 120 kilometers. In the time it takes to fall asleep, if you are lucky tonight and it takes 20 minutes, you will have moved 35,000 kilometers. That is nearly 3 times the diameter of the Earth. While lying in bed, without shifting position, every year you complete a circuit of 940 million kilometers and arrive back where you started, which is what a birthday actually is. A lap. Now, how do you find that out? Sitting on the thing that is doing it? The first solid detection was an accident, and it came from an astronomer trying to measure something else entirely. In the 1720s, James Bradley was trying to detect stellar parallax. The idea is straightforward. If the Earth moves around the sun, then a nearby star should appear to shift slightly against the distant background as we view it from opposite sides of the orbit, in the way your thumb held at arm's length appears to jump when you close one eye and then the other. Parallax would prove the Earth moves, and it would give the distances to the stars. Everyone wanted it. Nobody had found it because the stars are so far away that the effect is tiny. Bradley and a colleague set up a specially built telescope, fixed vertically in a house in Kew, to watch a star called Gamma Draconis pass directly overhead with extreme precision. They found a shift, and it was the wrong shift. Parallax should have peaked at particular times of year when the Earth was at the extremes of its orbit relative to the star. What Bradley saw was displaced by 3 months from that. The star was moving in a small annual ellipse, but out of phase with what parallax required. He puzzled over it for a long time, and the answer, according to the story, came to him on the Thames, watching a weather vane on a boat. As the boat changed direction, the vane shifted, even though the wind had not. The apparent direction of the wind depended on the boat's own motion. Light works the same way. If you are moving sideways while light arrives from above, you must tilt your telescope slightly forward into the motion, exactly as you tilt an umbrella when walking through vertical rain. He published in 1729. The effect is called the aberration of starlight. The angle is about 20.5 arcseconds, and it is a direct consequence of the ratio between Earth's orbital speed and the speed of light, which means Bradley had, without intending to, produced the first direct physical proof that the Earth moves around the sun, nearly 200 years after Copernicus and about 90 years after Galileo was tried for arguing it. That is layer 2. 29.8 kilometers per second, discovered by a man watching a weather vane. Layer 3 is smaller in magnitude and much larger in meaning, because it is the first one that is not a closed loop. The sun is not sitting still while the Earth goes round it. The sun is moving through the local neighborhood of stars, and it is heading toward a point in the constellation Hercules, near the border with Lyra, not far from the bright star Vega. Astronomers call that point the solar apex. The opposite point, which we are moving away from, is the antipex, down in Columba in the southern sky. The speed is about 20 kilometers per second relative to the average motion of the stars around us. And the way this was found is, for me, the single most impressive piece of reasoning in tonight's episode, because it was done in 1783, with no photography, no spectroscopy, no way to measure a star's velocity directly, and with data that was barely adequate. William Herschel had a table of proper motions. Proper motion is the slow, apparent drift of a star across the sky over years and decades, and by the 1780s, a handful had been measured, each one tiny, a fraction of an arc-second per year. Herschel reasoned as follows. If the sun is moving through a swarm of stars, then from our perspective, the stars ahead of us should appear to spread apart, opening outward the way scenery opens up as you walk toward it. And the stars behind us should appear to close together, converging the way a road narrows behind you. So he took his handful of measured proper motions and looked for that pattern, a point on the sky from which the motions appeared to diverge. He found one in Hercules, with something like a dozen stars, imprecise measurements and pure geometry. He identified the direction the entire solar system is traveling, and modern measurements from spacecraft with 1 billion stars in their catalog put it within a few degrees of where he said, "There is something wonderful about that. The direction we are going was worked out from a garden in Bath before anyone knew what a galaxy was. And this layer is different in kind from the first two, which is worth pausing on. The spin comes back around every day. The orbit comes back around every year. They are closed. You return. The sun's motion toward Hercules does not come back. We have never been where we are now, and we will never return to it. This is the first layer that is one way. Let me give you an image for what we are building, because the layers are about to get much larger, and I want you to have something to hold. Picture someone asleep on a night train. They are in a bunk in a dark compartment, and they are entirely still. Nothing about them is moving. They are as motionless as a person can be. The train is doing 140 kilometers an hour through the dark. The train is on a ferry, and the ferry is crossing a strait at 30 kilometers an hour in a direction that is not quite the same as the train's. The ferry is on an ocean, and the ocean has a current, and the whole body of water is drifting slowly along the coast. The coast is on a continental plate, and the plate is sliding a few centimeters a year against its neighbor. And every part of this is real, and every part of it is happening simultaneously, and the sleeping person feels precisely none of it, and would give you the same answer if you woke them and asked whether they were moving. No, I am lying still. And they would not be wrong exactly. Relative to the bunk, they are perfectly still. That is a true and useful description of their situation, and it is the one that matters if they want to know whether their tea will spill. It is simply not the only true description, and it is not the deepest one. That is our situation tonight, with one difference. The sleeping passenger, if they got up and opened a window, could see the landscape going past and settle the matter. We cannot open a window. There is no landscape. So we have been forced to work out our own motion in a much harder way. And every layer we have added tonight came from someone finding an ingenious sideways route to an answer they could not simply look at. Right, layer 4, and this is the big one. The whole thing we have described so far, the spinning Earth, its orbit, the sun drifting toward Hercules with its whole family in tow, is itself in orbit around the center of a galaxy. We are about 26,000 light years from that center, which puts us a little over halfway out from the middle of a disk, roughly 100,000 light years across, and we are traveling around it at approximately 230 kilometers per second. Let me try to make that number physical, because it is the fastest thing in tonight's stack that is still, in a sense, local. 230 kilometers per second is around 830,000 kilometers per hour. It would take you from the Earth to the Moon in under half an hour. It is fast enough to cross the entire continental United States in about 20 seconds. In the time it takes to say a single sentence, you have moved 1,000 kilometers, and the lap takes somewhere in the region of 230 million years. That is the number I find most affecting in the whole of tonight. The last time the solar system was in this part of the galaxy, the first dinosaurs were beginning to appear. The Atlantic Ocean did not exist. All the land on Earth was joined into a single continent. 1 galactic year ago. 1 lap. The sun has completed perhaps 20 of these in its lifetime. Human beings as a species have existed for roughly 1,000th of a single lap. Now, working this out is a genuinely hard problem because we are inside the thing, and the history of solving it is the history of people slowly realizing how badly placed they were. For most of history, the Milky Way was a band of light, and nobody knew what it was. Galileo turned a telescope on it in 1610 and found that it resolves into countless individual stars, which was the first real clue. By the early 20th century, the picture was that the Milky Way was the universe, that it was a lens-shaped collection of stars, and that the sun sat somewhere near the middle of it. That last part felt natural because when you count stars in every direction, you get roughly the same number, which suggests you are central. That was wrong, and the reason it was wrong is dust. The galactic plane is full of interstellar dust, and dust blocks visible light effectively. When you look along the plane, you cannot see very far before your view is cut off in every direction, which produces exactly the illusion of being at the center of a smaller system than you are actually in. You are in a fog, and the fog looks the same all around. The person who broke it was Harlow Shapley in 1918, and the method was to look at things above and below the dust. Globular clusters are dense spherical swarms of hundreds of thousands of old stars, and they orbit in a roughly spherical halo rather than sitting in the disk, which means many of them are visible above and below the murk. Shapley measured distances to a large number of them using variable stars inside them as standard candles, and noticed that they are not evenly distributed around the sky. They pile up strongly toward the constellation Sagittarius. His reasoning was that the clusters should be arranged symmetrically about the center of the galaxy, so if they appear off to one side, we must be off to one side. He put the center in Sagittarius and moved us out to the suburbs. He overestimated the distance because he had not accounted for how much the dust dims things, but the shape of the answer was right, and it was one of the great demotions in the history of astronomy. Then, in the 1920s, the Dutch astronomer Jan Oort did something harder. He worked out how fast we are going round. The method, developed alongside Bertil Lindblad's theoretical work, is called differential rotation, and the insight is that a galaxy does not turn like a solid record. Stars closer to the center orbit faster than stars further out. So from our position, stars slightly inside our orbit slowly pull ahead of us, and stars slightly outside slowly fall behind. Measure that systematic pattern across many stars, and you can extract the rotation of the whole disk, including our own speed, from inside it. Oort published in 1927. 2 numbers that came out of it are still called the Oort constants, and modern work has refined it with extraordinary precision. Radio observatories using very long baseline interferometry, essentially linking dishes across continents to make one enormous instrument, have measured the parallaxes of star-forming regions across the galaxy directly, and the Gaia spacecraft has measured positions and motions for well over 1 billion stars. The current best figures put us at roughly 26,000 light years out, moving at somewhere around 220 to 240 kilometers per second, with the uncertainty being honest rather than trivial. And there is one more thing about this rotation that has to be mentioned, because it changed cosmology. If you measure how fast stars orbit at different distances from the galactic center, you get a rotation curve. And based on the visible matter, that curve should fall off as you go outward, the way planets in the solar system orbit more slowly the further out they are, because almost all the mass is concentrated in the middle. It does not fall off, it flattens. Stars in the outer regions of galaxies orbit far faster than the visible matter can account for. Vera Rubin, working with Kent Ford in the 1970s, measured this carefully in Andromeda and then in dozens of other galaxies, and found the same flat curve every time. Either gravity does not work as we think at those scales, or there is a great deal of matter out there that we cannot see. Fritz Zwicky had proposed something similar in 1933 from the motions of galaxies in the Coma cluster, and been largely ignored for 40 years. Rubin's rotation curves were what finally made the field accept it. So the speed at which you are being carried around the galaxy tonight is itself evidence for dark matter, which makes up around 85% of the matter in the universe, and which nobody has directly detected. Layer 4, 230 kilometers per second, 230 million years to the lap, and a mystery attached to it. And it is worth saying what we are actually going around, because that answer arrived recently, and it took 26 years of patient watching. The center of the galaxy is hidden. It sits behind roughly 30 magnitudes of dust extinction in visible light, which means something like 1 visible photon in 1 trillion gets through. For most of the 20th century, it was simply a direction, not a place. Radio astronomy got there first. In 1974, Bruce Ballack and Robert Brown found a compact, very bright radio source at the exact center, and it was named Sagittarius A star, with the star pronounced as the word rather than the symbol. But a radio source is not an identification. The question was what it is. 2 teams took it on, one led by Reinhard Genzel in Germany and one by Andrea Ghez in the United States, and their approach was the only one available. Track the individual stars orbiting the center and watch what their orbits reveal about the mass they are going around. That is enormously difficult. The stars are 26,000 light years away, obscured by dust and crowded together. It required working in the infrared, which penetrates dust far better, and it required adaptive optics, where a telescope's mirror is deformed hundreds of times per second to cancel the blurring of the atmosphere, and it required patience because orbits take time. They watched from the early 1990s onward. Slowly, star by star, the orbits emerged. One star in particular, cataloged as S2, turned out to be on a tight ellipse with a period of about 16 years, sweeping in to within about 17 light hours of the center at closest approach and moving at several thousand kilometers per second when it did. By 2002, they had watched S2 through its closest approach. By 2008, they had a full orbit, and an orbit gives you the mass inside it, precisely by the same reasoning that gives you the mass of the sun from the Earth's year. The answer is about 4 million times the mass of the sun, packed into a region smaller than the orbit of Mercury. There is nothing that can be except a black hole. Genzel and Ghez shared the Nobel Prize in 2020 for it. Ghez was only the 4th woman ever to receive the physics prize, and in May of 2022, the Event Horizon Telescope collaboration released an image of it, produced by linking radio dishes across the planet into a single instrument the width of the Earth, a fuzzy orange ring around a dark center, which is the shadow of the event hole against the glow of matter around it. So the thing we've been circling for 230 million years, the thing every one of us is going around at this moment, is a black hole 4 million times the mass of the sun. And it is quiet. It is not devouring anything dramatic. It is accreting very slowly and glowing faintly, and it has been sitting there since long before the galaxy took its present shape. Layer 5 is small and slow and easy to miss, and I like it enormously. We are also bobbing. The sun's path around the galactic center is not a flat circle in the plane. It is also oscillating vertically, rising above the midplane of the disk, slowing, falling back through, descending below, slowing again, and rising once more. The mechanism is simple and rather lovely. The mass of the galaxy is concentrated in the disk. When the sun is above the plane, all that mass is below it, pulling down. So the sun decelerates, stops, and falls back, accelerates through the middle, overshoots and finds itself below, with the mass now above, pulling up. It is a pendulum, and the disk of the galaxy is the restoring force. The same shape as Foucault's pendulum in the Pantheon, at a scale of thousands of light years and tens of millions of years. The numbers here are less settled than the others, and I would rather give you the honest range than false precision. The sun currently sits somewhere in the region of 50 to 60 light years above the midplane and is moving upward at about 7 kilometers per second. Estimates for the maximum height reached run from roughly 160 up to 300 light years, and for the full period from something like 50 to 95 million years, depending on the model and on assumptions about how mass is distributed in the disk. So our path through the galaxy is not a circle. It is a long, slow corkscrew, rising and falling a handful of times per galactic lap. There is a long-running and inconclusive line of research asking whether those crossings correlate with mass extinctions on Earth, the idea being that denser regions near the midplane might disturb the Oort cloud and send comets inward. Some papers find periodicities in the fossil record. Others find the periodicities are not statistically robust, or that the timings do not line up. It is an appealing idea without settled evidence, and I mention it mainly because you will encounter it. The bobbing itself is real regardless. Now let's do the arithmetic, and this is where most accounts of this subject go wrong, so I want to be careful. The obvious move is to add the numbers up. 460 meters a second for the spin, 29.8 kilometers a second for the orbit, 20 for the sun's local drift, 230 for the galaxy, something for the bobbing. Add them and you get a number somewhere around 280 kilometers per second, and you might feel you have your answer. You do not, and the reason is direction. These motions do not point the same way. The Earth's spin carries you east, and east is a direction that rotates completely once a day, relative to everything else. The orbital motion lies in the ecliptic plane. The galactic rotation lies in the galactic plane, which is tilted about 60 degrees to the ecliptic. The sun's drift toward Hercules is at yet another angle. Velocities are not quantities you add like sums of money. They are arrows, and adding arrows means placing them nose to tail and measuring the gap from the very start to the very end. Point two arrows in opposite directions and they cancel. Point them at right angles and the total is less than the sum. So for part of every day, the Earth's rotation is carrying you in roughly the direction of its orbit, and your total is slightly higher. 12 hours later, it is carrying you against it, and your total is slightly lower. You are speeding up and slowing down by about half a kilometer per second, twice a day, forever. The same is true at every scale. In June, the Earth's orbital motion partly aligns with the Sun's galactic motion and partly opposes it in December or thereabouts. The layers are not stacked neatly. They are running at every angle to one another, and the true total wanders as they turn, which means that if you want one honest number for how fast you are actually moving, you cannot get it by adding. You have to measure it, and to measure it, you need something to measure against. Which brings us to the question that has been quietly waiting since the first sentence. Moving relative to what? It sounds like a quibble, and it is the deepest question in classical physics. It occupied Newton, it occupied Leibniz, it occupied Ernst Mach, and it is a substantial part of what drove Einstein to general relativity. Here is the difficulty in its simplest form. Every speed we have named tonight was relative to something. 460 meters a second relative to the Earth's axis, 29.8 relative to the Sun, 20 relative to the neighboring stars, 230 relative to the galactic center. Each of those reference points is itself moving relative to something else. So the chain continues, and the question is whether it ever stops. Is there such a thing as being genuinely at rest, or is motion only ever a relationship between two things with no absolute answer underneath? Newton was certain there was an answer. In the Principia in 1687, he asserted the existence of absolute space, which he described as remaining always similar and immovable, without relation to anything external. Motion relative to that space was real motion, and everything else was merely relative. And he offered an argument, which is one of the most famous thought experiments in physics, and it involves a bucket. Take a bucket of water, hang it from a twisted rope, and let go. At first, the bucket spins and the water does not. Friction has not caught up yet. The water surface stays flat. So here you have relative motion between the bucket and the water and a flat surface. After a while, the water catches up and spins with the bucket. Now there is no relative motion between them at all. And the water surface is curved, climbing the sides, dished in the middle. Now grab the bucket and stop it. The water keeps spinning. Relative motion again, and the surface is still curved. So the shape of the water does not depend on its motion relative to the bucket. Then relative to what? Newton's answer: relative to absolute space. The water climbs the walls because it is genuinely rotating in an absolute sense, and rotation is therefore a real and detectable thing rather than merely a relationship, which was a strong argument. And it held for 2 centuries, and it always made people uncomfortable because absolute space could not be observed. It was invisible, undetectable, and did nothing except serve as the thing everything else was measured against. The most interesting objection came from Ernst Mach, an Austrian physicist and philosopher, in the 1880s. Mach said, Newton's experiment does not show what he claims. When the water climbs the walls of the bucket, it is not rotating relative to nothing in particular. It is rotating relative to the fixed stars, relative to all the matter in the universe. And, Mach suggested, that might not be a coincidence. Perhaps inertia itself, the resistance of matter to being accelerated, arises from the gravitational influence of all the distant matter in the universe. take the stars away, and the water would not know it was spinning and would not climb. He put it in a way that has been quoted ever since. It makes no difference whether we think of the Earth as turning round on its axis or at rest, while the fixed stars revolve around it. This idea, which Einstein later named Mach's principle, has never been fully formalized or fully proven, and it has never gone away. Einstein said explicitly that it was one of the things that motivated him toward general relativity, and general relativity contains echoes of it, most notably frame dragging, where a rotating mass genuinely drags space-time around with it. Gravity probe B, launched in 2004, measured that effect around the Earth and found it as predicted. But whether Mach's principle is fully realized in general relativity is still argued about, which is remarkable for an idea from the 1880s. Now, Einstein's own contribution to this question is easily misunderstood. So, let me be precise. Special relativity in 1905 did not say everything is relative. It said something much sharper. It said the laws of physics are the same for all observers moving at constant velocity, and the speed of light is the same for all of them. And therefore, there is no experiment that can single out one state of uniform motion as the true rest. That killed absolute space in the sense Newton meant it. And it also killed the luminiferous ether, which was the 19th century's version of the same idea. The medium light was supposed to wave in. So after 1905, there is no universal rest frame. There is no experiment that will tell you that you, specifically, are the one truly standing still, which appears to end the question with a no. And it is worth telling the ether story properly, because it is the closest anyone came to answering tonight's question the wrong way, and the failure was more useful than a success would have been. Through the 19th century, light was understood as a wave, and waves were understood to be disturbances in a medium. Sound waves in air, ripples in water. So light waves must be disturbances in something, and that something was named the luminiferous ether. It had to have peculiar properties. It filled all of space, including the space between the stars. It had to be extremely rigid because the speed of light is enormous, and waves travel fast in stiff media, and yet it had to offer no resistance whatsoever to planets moving through it, since the Earth has been going round the sun for billions of years without slowing. Nobody was comfortable with it. But if it existed, it provided exactly what we have been looking for all night: a fixed stage, a universal frame, something absolutely at rest. And it should have been detectable. If the Earth is moving through the ether, then light traveling in the direction of that motion should behave differently from light traveling across it, in the same way that swimming upstream and back takes longer than swimming the same distance across a river and back. In 1887, at what is now Case Western Reserve University in Cleveland, Albert Michelson and Edward Morley set out to measure it. The instrument was extraordinary for its time. A beam of light split in two, sent along perpendicular arms, bounced back by mirrors, and recombined. If one beam took slightly longer than the other, the recombined light would show interference fringes, and the position of those fringes would shift as the apparatus was rotated. To keep it stable, they mounted the whole thing on a large stone slab, floating in a trough of mercury, so it could be turned smoothly without vibration. Michelson had built earlier versions and knew how sensitive it needed to be. They expected a clear shift. They found essentially nothing. They repeated the measurement at different times of year, in case the Earth happened to be momentarily at rest with the ether in one season, and still found nothing. It is the most famous null result in physics, and it is the reason the ether had to go. There were attempts to save it. George Fitzgerald and Hendrik Lorentz independently proposed that objects moving through the ether contract slightly along the direction of motion by exactly the amount needed to hide the effect, which works mathematically and is deeply unsatisfying as physics because it amounts to proposing that nature conspires to keep the thing undetectable. Einstein's move in 1905 was to stop trying to save it. If no experiment can detect motion through the ether, perhaps the reason is that there is nothing to detect. Take the constancy of the speed of light as a starting assumption rather than a puzzle, and the length contraction and time dilation fall out as consequences rather than excuses, so the ether was abandoned, and with it the last version of Newton's absolute space. And I find it worth noting what that means for tonight. The 19th century looked for a universal frame and did not find one. The 20th century then found something that functions as a natural frame anyway, not by being a medium that light waves in, but simply by being the average rest state of the matter and radiation that happens to fill the universe. Not absolute, not required by any law, just there and measurable, and the same for everyone, which is a better answer than the ether would have been because it is one you can actually point an instrument at. Except there is a difference between a law of physics and a piece of furniture. Special relativity says the laws are the same in every frame. It does not say the universe looks the same from every frame. And it turns out the universe is full of something spread almost perfectly evenly through all of space, and that something provides a frame you can measure yourself against. Not a violation of relativity and not an absolute rest frame in Newton's sense, just a natural one, the frame in which the contents of the universe on the largest scales are at rest. And we found it by accident because two engineers could not get rid of a noise. In 1964, at Bell Telephone Laboratories in Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson had been given the use of a large horn-shaped antenna. It had been built for bouncing radio signals off early communication satellites and was no longer needed for that, so they had converted it for radio astronomy. And the first thing they needed to do was calibrate it. That meant finding and eliminating every source of noise in the system so they would know what a genuinely quiet sky sounded like. They could not get rid of one. There was a faint, persistent hiss corresponding to a temperature of about 3.5 degrees above absolute zero, and it would not go away. It did not change when they pointed the antenna in different directions. It did not change with the time of day, which ruled out anything on Earth rotating past. It did not change with the seasons, which ruled out anything in the solar system. It was not the Milky Way because it did not brighten when they looked along the galactic plane. They spent the best part of a year trying to eliminate it. They checked the electronics. They checked the joints. They found that a pair of pigeons had been roosting in the horn and had coated the inside with what Penzias later described, in a phrase that has followed the story ever since, as a white dielectric material. They evicted the pigeons, they cleaned the horn, they taped over the rivets. The hiss remained exactly as before. Meanwhile, about 60 kilometers away at Princeton, a group led by Robert Dick was preparing to search for exactly this. The theoretical prediction went back to work in the 1940s by George Gamow, Ralph Alpher, and Robert Herman, who had reasoned that if the universe began in a hot, dense state, then in the early moments it would have been an opaque plasma. And as it expanded and cooled, there would come a point where electrons and nuclei combined into neutral atoms, and the fog cleared and light streamed out freely in all directions. that light would still be traveling, stretched enormously by the expansion of space in the billions of years since, so that it now arrives not as visible light, but as microwaves at a temperature of a few degrees above absolute zero, coming from every direction at once. Alpher and Herman published an estimate in 1948, and essentially nobody followed it up. The prediction sat unregarded for 15 years. Dicke's group had reconstructed the idea independently and were building a detector. Then a mutual acquaintance connected them with the two engineers in New Jersey who had a noise they could not remove. Dicke reportedly put down the phone and told his colleagues that they had been scooped. The two groups published side by side in 1965. Penzias and Wilson's paper is famously modest, titled as a measurement of excess antenna temperature, with the interpretation left to the companion paper by Dicke and his colleagues. Penzias and Wilson received the Nobel Prize in 1978, and what they had found is the oldest thing anyone can see: the cosmic microwave background, light released about 380,000 years after the beginning, when the universe first became transparent, still arriving from every direction, filling all of space. Its temperature is 2.725 Kelvin, and when you look at it in detail, it is astonishingly uniform. After you account for one thing, the variations are about 1 part in 100,000. That one thing is what tonight has been building toward. Because the cosmic microwave background is not quite the same temperature in every direction. There is a pattern in it, and the pattern has a very particular shape. It is warmer in one direction and cooler in the exactly opposite direction, with a smooth gradient in between. One hot spot, one cold spot on opposite sides of the sky. Astronomers call that shape a dipole. The size of it is about 3.5 thousandths of a Kelvin either way. Roughly 1 part in 1,000, which makes it about 100 times larger than everything else in the map. It was detected properly in 1977 by a group including George Smoot, using a differential radiometer flown on a U-2 aircraft to get above most of the atmosphere. And the explanation is beautifully simple. It is a Doppler shift. You know Doppler shift from sound. A siren approaching you sounds higher and drops in pitch as it passes and recedes, because your motion relative to the source compresses or stretches the waves. Light does the same. If you move toward a source of radiation, its wavelengths are slightly compressed, which for a thermal spectrum means it appears slightly hotter. Move away, and it appears slightly cooler. So if the cosmic microwave background genuinely fills all of space uniformly, and you are moving through it, you will see it as slightly hotter in the direction you are heading and slightly cooler behind you. Exactly one hot spot and one cold spot, exactly opposite each other, with a smooth gradient between. Exactly what is observed, which means the dipole is not a feature of the universe, it is a feature of us. It is a picture of our own motion, painted onto the oldest light there is. And the size of the temperature difference gives you the speed. Here is the answer. The solar system is moving at approximately 370 kilometers per second relative to the cosmic microwave background. That is the number. That is how fast you are moving, in the only sense that has ever been made precise. Not relative to your bed or the ground or the sun or the galactic center, but relative to the average rest frame of the contents of the universe. 370 kilometers every second, around 1 1/3 million kilometers per hour, about 1,000th of the speed of light. in the direction of the constellation Leo, which in the northern spring is high in the evening sky. Now notice something about that number because it is the point I flagged earlier, and it is the reason we did the arithmetic carefully. 370 is not the sum of the layers. It is not far off the galactic rotation figure of 230, but it is not that either. It is a genuine vector total. All the layers combined at all their various angles, and it comes out where it comes out. Now, one honest caveat about that number, because it is not simply read off a dial. Getting the dipole out of the sky is harder than it sounds, for the same reason the great attractor was hidden. Our own galaxy is in the way. The Milky Way glows in microwaves. Dust in the galactic plane emits, electrons spiraling in magnetic fields emit, ionized gas emits, and all of that lies across the middle of every all-sky map like a bright band. It is far stronger than the tiny signal underneath it, so the process is one of careful subtraction. You observe at many different frequencies, because the galaxy's emission changes with frequency in characteristic ways, while the cosmic background does not, being a thermal spectrum. Then you model each foreground component and remove it, and what remains should be cosmological. That is delicate work, and it is where most of the effort in the field goes. There is also a question that has been raised in the last decade or so, and it is unresolved enough to be worth mentioning honestly rather than tidying away. If the dipole is entirely due to our motion, then that same motion should produce a matching effect in the distribution of distant objects. Moving through the universe should make galaxies appear very slightly more numerous in the direction you are heading, an effect predicted by James Ellis and John Baldwin in 1984. Several studies using catalogs of radio sources and quasars have found that the dipole in the counts of distant objects points in roughly the right direction, but is noticeably larger than the CMB dipole would predict. That could mean a subtlety in the source catalogs, which is many people's expectation. It could mean the local universe has genuine large-scale structure in it beyond what the standard model comfortably allows. Or it could mean something about the cosmological principle, the assumption that the universe is the same everywhere. Needs refining. It is an open question, and the honest position is that nobody knows yet. So the number I gave you, 370 kilometers per second, is solid and well measured. What it fully implies about the largest scales is still being worked out, which is a rather good state for a science to be in. And there is another number, one step up, which is the one I find most extraordinary. If you subtract out the sun's motion around the galaxy and the Milky Way's motion within our small cluster of galaxies, you can ask how fast the whole local group is moving relative to the cosmic microwave background. The local group is our galaxy, Andromeda, the Triangulum galaxy, and around 80 smaller ones spread across roughly 10 million light years and bound together by gravity. The answer from measurements refined over decades is around 630 kilometers per second. The whole thing. Every galaxy in our local neighborhood moving together in one direction at 630 kilometers a second. That is not something we inherited from any of the layers we counted. That is a motion of the entire structure, and it needs explaining. Something is pulling. The search for what is pulling us has been going on since the dipole was measured, and it is one of the more absorbing detective stories in modern astronomy, partly because the answer turned out to be hiding behind our own galaxy. The first serious attempt came in the 1980s from a group of 7 astronomers who worked together long enough and closely enough that the community started calling them the Seven Samurai. Donald Lyndon Bell, Sandra Faber, David Burstein, Roger Davies, Alan Dressler, Roberto Turlevich, and Gary Wegner. Their method was to measure how fast a large number of galaxies are actually moving, as distinct from how fast the general expansion of the universe should be carrying them. The overall expansion means distant galaxies recede, and the further away they are, the faster they recede. And that relationship is smooth and predictable. But individual galaxies also have their own motions on top of that, caused by the gravitational pull of whatever mass is nearby. Those extra motions are called peculiar velocities, and the word peculiar here means particular to that object rather than strange. If you can measure a galaxy's actual distance independently and compare it to the recession speed you observe, the difference is the peculiar velocity. They did that for hundreds of elliptical galaxies, and what they found in 1988 was that the galaxies were not moving randomly. They were streaming coherently over an enormous region, all in the same general direction. Something with an enormous amount of mass was pulling them, and it was in the direction of the constellation Centaurus. They called it the Great Attractor, which was frank rather than technical. Nobody knew what it was. And here is the frustrating part, and it is the same problem we met earlier with dust. The direction of the Great Attractor is almost exactly behind the plane of our own galaxy, at a galactic latitude of only a few degrees, which puts it in what astronomers call the zone of avoidance, the band of sky where the Milky Way's dust and stars block our view of everything beyond. Roughly a fifth of the sky is obscured that way. And the single most gravitationally significant thing in our neighborhood happened to be sitting in it. Progress came from going around the dust rather than through it. Radio surveys of neutral hydrogen, which passes through dust unimpeded. X-ray surveys, which find hot gas in galaxy clusters. Infrared surveys, which penetrate much better than visible light. Gradually, a picture emerged. There is a rich cluster there, Abel 3627, sometimes called the Norma cluster, close to the center of the flow. And behind it, much further out, at around 650 million light years, sits something considerably larger, the Shapley concentration, the most massive concentration of galaxies in the nearby universe, containing many clusters bound together. The current understanding is that the Great Attractor region is real, but is not the whole story. It is more like a local rise on a slope that continues much further, and a substantial part of the pull comes from Shapley beyond it. And then in 2017, a paper in Nature Astronomy by Yehuda Hoffman, Daniel Pomerade, Brent Tully, and Hélène Courtois added something that genuinely reframed the picture. They mapped the three-dimensional velocity field of the local universe using a large catalog of galaxy peculiar velocities, and reconstructed not just where things are, but which way everything is flowing. And they found that our motion is not driven by attraction alone. There is a region on the opposite side of the sky from the Shapley concentration, which contains far fewer galaxies than it should, an enormous underdense area, a void, and a void pushes. That sounds wrong, so let me be careful about it, because it is not a new force. Gravity only ever attracts. But consider what it means to be surrounded by matter that is unevenly distributed. If there is more mass on one side of you than the other, you are pulled toward the denser side. Equivalently, and this is the same statement, you are pushed away from the emptier side because the pull from that direction is weaker than average. Relative to the surrounding average, an underdense region acts as a repeller. The paper's finding is that this void, which they named the dipole repeller, and the Shapley concentration contribute roughly equally to the local group's motion. Half the flow is us falling towards something enormous. The other half is us drifting away from a place where there is not much of anything. The repeller sits at a distance of around 16,000 kilometers per second in redshift units, which is on the order of 700 million light years, and it is almost exactly anti-aligned with the direction of the flow, which is a lovely thing to know at the end of an accounting of your motion. You are being pushed by an absence. Before we leave the galaxy, there is something worth saying about the neighborhood we are moving through, because it is not fixed either. The Milky Way is a spiral, and spirals have arms. We sit near the inner edge of a modest one called the Orion arm, or sometimes the local arm, which for a long time was thought to be a minor spur between two major arms, and which more recent radio measurements suggest is longer and more substantial than that. But here is the thing about spiral arms, and it is not what most people picture. The arms are not made of a fixed set of stars that rotate together like the arms of a pinwheel. If they were, they would wind themselves up tight within a few galactic rotations, because the inner parts orbit faster than the outer parts. Galaxies would not still have open spiral patterns after 20 laps. The leading explanation, developed in the 1960s by Chia Chiao Lin and Frank Xu, is that the arms are density waves, regions where the orbits of stars and gas bunch up temporarily, moving through the disk at their own pace, distinct from the material passing through them. The usual analogy is a traffic jam on a motorway. The jam has a shape and a position, and it may drift slowly backward along the road, and yet no individual car stays in it. Cars enter the jam, slow down, spend a while in the congestion, and then emerge and speed away, while the jam itself persists. Stars do that with spiral arms. They drift in, linger because the density slows them, and drift out again, which means the arms are bright not because they contain more stars overall, but because the compression triggers star formation, and the brightest and shortest lived stars form there and die before they can travel far. The arms glow with the young ones. The sun passes through arms periodically on a timescale of 100 million years or so, and the details are not well settled, and the stars around us are not traveling with us in formation either. The sun was born in a cluster, alongside probably hundreds or thousands of siblings, and that cluster dissolved long ago as the differential rotation of the galaxy pulled it apart. Those siblings are now scattered right around the disk, chemically similar to us and effectively impossible to identify with confidence. So the stars you see tonight are not companions. They are traffic, passing at various speeds and various angles. Barnard's star, 6 light years away, has the largest proper motion of any star known and crosses an apparent distance equal to the width of the full moon every 180 years or so. Arcturus, one of the brightest stars in the northern sky, is moving at over 100 kilometers per second relative to us, much of it perpendicular to the galactic plane, because it is an old halo star on a steeply tilted orbit simply passing through our neighborhood on its way somewhere else. And in around 40,000 years, a small dim star called Gliese 710 is expected to pass within about a fifth of a light year of the sun, which is far closer than any star is now, and close enough to pass through the outer Oort cloud. The constellations themselves are dissolving slowly. Every figure you can name in the sky is a chance alignment of stars at different distances moving in different directions, and given enough time they all deform. The plow will not be a plow in 100,000 years, the handle will bend because 5 of its 7 stars are moving together as a group, and the 2 on the ends are not. So the picture is not one of us moving through a fixed backdrop. It is of everything moving through everything else, at every scale, all the time, with the appearance of permanence coming entirely from the shortness of a human life. Before we go up another level, there are 2 motions between the galaxy and the largest scales, and they are worth separating carefully because one of them is not really a motion at all. The first one is straightforward. The Milky Way is not alone. Our galaxy belongs to a small cluster called the local group, which contains something like 80 known members spread across roughly 10 million light years. Most of them are small. 2 are large, our own, and Andromeda, which sits about 2.5 million light years away and is the most distant thing the unaided human eye can see. A faint smudge in the autumn sky that people have been noticing since at least the 10th century. Everything in the local group orbits a common center of mass, which lies somewhere between us and Andromeda, and the Milky Way is moving within that group. The figure is somewhere in the region of 100 to 130 kilometers per second toward Andromeda, because Andromeda is coming toward us. That deserves a moment, because almost everything else in the universe is receding. Andromeda is approaching at around 110 kilometers per second, and in roughly 4 to 5 billion years, the 2 galaxies will collide. Collide is a slightly misleading word. Almost no stars will hit anything. The distances between stars are so vast that the 2 galaxies will pass largely through one another, with the gas clouds colliding and compressing and triggering an enormous burst of star formation, and the orbits of everything scrambled by the gravitational disturbance. They will separate, fall back, pass through again, and eventually settle into a single large elliptical galaxy. The sun will probably survive it, most likely flung out to a wider orbit. Earth will not be habitable by then for entirely unrelated reasons. So that motion is real, and it is gravitational, and it belongs in tonight's stack. The second thing is different, and it is the one people most often mix up with motion. Space is expanding. Since Edwin Hubble's work in 1929, building on Vesto Slipher's earlier measurements of galaxy redshifts and Georges Lemaitre's theoretical work in 1927, we have known that distant galaxies are receding from us, and that the further away they are, the faster they recede in a smooth, proportional relationship. The natural reading is that everything is flying apart from an explosion with us near the middle. That reading is wrong on both counts. Galaxies are not, for the most part, moving through space away from us. The space between them is increasing. The standard picture for this is a loaf of raisin bread rising in an oven. Every raisin gets further from every other raisin, and from the point of view of any raisin, all the others appear to be receding, and the distant ones recede faster because there is more expanding dough between you and them. No raisin is at the center. No raisin is moving through the dough, which is why there is no center of the universe to point at and no edge to fall off, and why every observer everywhere sees the same recession. And crucially, for tonight's purposes, that expansion is not something you can be moving with or against. It is not a current. It has no direction. It does not contribute a velocity to your total. The cosmic microwave background dipole measures your motion relative to the local rest frame of the universe and it does not measure the expansion at all. Those are separate things, and conflating them is the single most common error in popular accounts of this subject. The expansion also does not affect anything held together. It does not stretch atoms or your body or the Earth or the solar system or even the local group. Gravity within a bound structure is enormously stronger than the tendency of space to expand at those scales, so bound things simply stay bound. The expansion is only visible between structures that are far enough apart to have nothing holding them together. So Andromeda is genuinely approaching, and the galaxies of the local group are genuinely bound, and the expansion is happening between our group and the ones far beyond it, and none of that is a speed you carry. And once you know the dipole is your own motion, something interesting follows. You can remove it, subtract the dipole from the map, and what is left is the universe with your own movement taken out of the picture. The view from a frame at rest with the contents of the cosmos. That subtraction is one of the most productive operations in the history of cosmology because of what turned up underneath. In November of 1989, NASA launched a satellite called COBE, the Cosmic Background Explorer, with George Smoot leading one instrument and John Mather leading another. It carried liquid helium to cool its detectors, and it mapped the whole sky. The first result, announced in January of 1990, was the spectrum. Mather's instrument compared the cosmic background to a reference source inside the satellite and found that it matches the theoretical curve for a perfect thermal emitter more precisely than any spectrum ever measured in nature. When it was shown at a conference, the audience gave it a standing ovation, which is not a normal response to a graph. The second result took 2 more years, and it was the one everyone was waiting for. After removing the dipole and after carefully subtracting the glow of our own galaxy across the middle of the map, there remained a faint mottling, patches very slightly warmer and very slightly cooler than average at the level of about 1 part in 100,000. Those are the seeds. The early universe was very nearly uniform, but not perfectly so, and the slight overdensities were pulled together by gravity over billions of years into everything that exists. Every galaxy, every star, every planet, every atom of you grew out of one of those faint patches. If the map had been perfectly smooth, nothing could have formed, and there would be nobody to look at it. The modeling had to be there, and finding it was a genuine relief. Smoot and Mather shared the Nobel Prize in 2006. 2 more satellites followed. WMAP, launched in 2001, and Planck, launched by the European Space Agency in 2009, each mapping the same sky at higher resolution and greater sensitivity. From the detailed statistics of those patches, cosmologists have extracted the age of the universe, its overall geometry, and the proportions of ordinary matter, and dark energy in it. A very great deal of what we claim to know about the universe comes from studying a pattern of temperature variations of 100,000th of a degree on a map from which our own motion had first to be carefully removed, which is worth noticing. Before you can see the universe clearly, you have to subtract yourself from the picture. And there is one more piece of local geography worth knowing, because it explains something about the direction we are traveling. The local group does not sit in empty space. It sits in a flattened sheet of galaxies, a structure sometimes called the local sheet, only a few million light years thick and tens of millions of light years across, and almost all of the nearby galaxies lie within it. That flatness is characteristic. On the largest scales, the universe is not a random scatter of galaxies. It is a web. Galaxies gather along filaments and spread across sheets, and between them are enormous voids with very little in them. The mass is concentrated on the walls in the way soap film concentrates on the boundaries between bubbles. We are on a wall, and our motion has a component that is perpendicular to that sheet, pushing us away from a large void that sits on one side of it, the local void, which is one of the emptier regions in our vicinity, and which is estimated to be tens of millions of light years across. The measurement of that particular component was made by Brent Tully and colleagues, who found that the local sheet is moving away from the local void at something in the region of 260 kilometers per second. So even before you get out to Shapley and the dipole repeller, the same principle is at work locally. Part of our motion is us being pushed off the edge of an emptiness that happens to be nearby. The voids are not passive. They are not simply where the galaxies are not. Because matter continues to drain out of them into the surrounding walls, they behave, relative to the average, as if they push. And here is the thing I keep returning to about that. If you drew an arrow showing which way you are going tonight, a substantial fraction of its length would be accounted for by regions containing nothing at all. You are being moved by absences. There is one more level up, and then we stop. In 2014, a team led by Brent Tully mapped the motions of 100,000 galaxies and asked a different question. Not where is the mass, but which galaxies are flowing together. If you follow the streamlines, the way you might trace the watershed of a river system, you find the galaxies naturally divide into basins of attraction. Everything in one basin is flowing toward a common region. They defined a supercluster as everything within one such basin and mapped ours. It is about 520 million light years across, contains something like 100,000 large galaxies, and the Milky Way sits out near one of its edges. They named it Laniakea from Hawaiian, meaning immeasurable heaven. And here is what that means for tonight's accounting. There is a layer above the galaxy. Our galaxy is flowing within the local group. The local group is flowing within a larger structure, and that structure is flowing toward the great attractor region and onward toward Shapley, while being pushed from behind by an enormous emptiness. That is layer 6, and it is the last one we can currently measure. Whether there is a layer 7 is an open question. The bulk flow appears to continue out to very large distances, and whether it eventually settles down to zero relative to the cosmic microwave background, or keeps going in ways that are not fully explained, is genuinely debated in the literature. Some measurements suggest larger flows on larger scales than the standard model comfortably predicts, which means the honest ending to the accounting is not a full stop. It is a question mark at the largest scale anyone has been able to look. So let me gather it all up gently because it is getting late. Here is what you are doing at this moment, lying still. You are turning with the Earth at up to about 460 meters a second, depending on your latitude, completing a circle once a day. You are orbiting the Sun at 29.8 kilometers a second, completing a circle once a year. You are drifting with the Sun toward the constellation Hercules at about 20 kilometers a second and not coming back. You are being carried around the center of the galaxy at roughly 230 kilometers a second, and the lap will take another 230 million years. You are bobbing slowly up through the plane of the galaxy at about 7 kilometers a second on an oscillation measured in tens of millions of years. And the whole structure you belong to, every galaxy for tens of millions of light years around, is streaming at around 630 kilometers a second towards something dense and away from something empty. Your own net motion relative to the oldest light in the universe, all of it combined at all its various angles, is about 370 kilometers a second toward Leo. Every one of those is happening simultaneously. Every one of them is real in the sense that it is measurable and consequential and correct. Not one of them is detectable by any sense you possess. And not one of them is the last word, because each one is measured against something that is itself in motion all the way up to a frame defined by radiation released before there were any stars at all. And there is a set of motions we have not counted at all because they are going in the opposite direction. Not outward through larger and larger structures, but inward. You are not still on the inside either. Your heart is beating, which you can feel if you attend to it, and beneath it there is a great deal you cannot. Every red blood cell in your body completes a circuit of the whole system roughly once a minute. Blood leaves the heart at around 0.5 meter per second in the aorta and slows dramatically as it spreads into smaller and smaller vessels, until in the capillaries it is creeping along at well under 1 millimeter per second, which is the speed it has to be for oxygen to have time to cross into the tissue. There are something on the order of 37 trillion cells in you, and inside each of them the traffic is constant. Motor proteins walk along filaments carrying cargo 1 molecular step at a time. Molecules of every kind are in continuous random motion simply from heat, colliding, rebounding, and drifting in what is called Brownian motion. That, incidentally, is the same phenomenon Einstein analyzed in 1905 in one of his 4 great papers, showing that the jittering of pollen grains in water was direct evidence that atoms exist, which was still genuinely in doubt at the time. At room temperature, an individual water molecule is moving at something like 600 meters per second between collisions. Faster than sound. It goes almost no distance before hitting something, which is why the water sits still in the glass. But each molecule is moving very fast indeed. The atoms in the walls of your room are vibrating in place, billions of times per second. Temperature is nothing but the name we give to that motion. Absolute zero is the point where it would stop, and nothing anywhere has ever reached it. So the picture inverts nicely. Look outward, and you find yourself carried by motion so vast and smooth that no sense could register them. Look inward, and you find yourself made of motion so small and so fast that no sense could register those either. And you sit in the narrow band, in between where things appear to hold still, which is the only band a body could have evolved to perceive. Slow enough to hold, fast enough to matter. Stillness is not a property of the universe. It is a property of the scale you happen to be built at. There is one more consequence of all this motion, and it is small enough to be charming rather than alarming. If special relativity is right, and it is one of the best tested theories we have, then moving clocks run slow. Not apparently. Actually, a clock in motion, relative to you, ticks at a slower rate, and the effect grows with speed. At everyday speeds, it is unmeasurably tiny. At 370 kilometers per second, which is about 1,000th of the speed of light, it is still very small, but it is not zero. The factor works out at around 1 part in 2 million, which means that if you could compare your clock to one at rest in the cosmic microwave background frame, yours would be running slow by roughly a second and a half per year. Over a human lifetime, perhaps 2 minutes. You have lived about 2 minutes less than someone who was genuinely at rest with the universe would have, purely from being carried along with everything else. There is nobody to compare with, of course, and no way to notice, and it makes no difference to anything. But it is a real effect, and it is being applied to you continuously. The same physics is applied deliberately every day in a system you probably used this week. The satellites of the Global Positioning Network carry atomic clocks, and they orbit at around 14,000 kilometers per hour, which makes their clocks run slow by about 7 microseconds a day from motion. They are also higher in Earth's gravitational field, and general relativity says clocks run faster where gravity is weaker, which speeds them up by around 45 microseconds a day. The net effect is about 38 microseconds a day of gain. That sounds trivial, and it is not. Position is worked out by timing signals traveling at the speed of light, and light covers about 300 meters in a microsecond. Ignore the correction, and your position would drift by roughly 10 kilometers per day. So the clocks are deliberately built to tick at a slightly wrong rate before launch, so that once they are up there and moving and higher in the gravity well, they tick correctly. Every navigation app on Earth works because two theories from 1905 and 1915 are being applied continuously to a fleet of clocks in orbit, which is a reasonable answer to anyone who wonders whether any of tonight is practical. Now, I have been calling these layers all night, and I want to say something about that word before we finish. It's because there is a temptation to hear all this as a story about being small, and I do not think that is what it is at all. Consider what it actually took to find each one. Nobody could feel any of them. Not one. Every single motion in tonight's list is invisible from inside, exactly as Galileo's cabin promised, and every one of them was worked out anyway by people who could not step outside and look. Foucault hung a weight from a dome and watched a line move in sand, and that was the planet. Bradley tilted a telescope into the rain of starlight and found the orbit while looking for something else and being annoyed about the result. Herschel took a dozen imprecise measurements of stars drifting and found the direction the whole solar system is traveling from a garden before anyone knew what a galaxy was. Shapley counted globular clusters above the dust and moved us out of the center. Oort measured stars slipping ahead and falling behind and extracted the rotation of a galaxy from inside it. Two engineers could not get a hiss out of an antenna, cleaned pigeon droppings out of it, and had found the oldest light in existence. And a group of astronomers mapped the flow of 100,000 galaxies and discovered that half of what moves us is a place with nothing in it. Every one of those is a person working out something they could not perceive, using something they could. That is the whole of science in a sentence, and this subject shows it more clearly than most, because there was never any possibility of simply looking. And there is a second thing, which is about the word still. Nothing tonight makes the sentence "I am lying still" false. Relative to your bed, you are not moving. That is true. It will still be true in the morning. Every practical question you have ever asked about your own motion has been answered correctly by that frame, and none of the numbers in tonight's list would have helped you catch a bus. What the layers tell you is not that stillness is an illusion. It is that stillness is a relationship and that you get to choose which relationship you mean, and that no choice is more correct than another for the purposes it serves. Physics does not have a privileged frame. That was the whole content of 1905. What it has is a natural one provided by the fact that the universe happens to be full of a very old, very even glow which anyone anywhere could measure themselves against. And relative to that glow, you are moving at 370 kilometers per second. Both of those are the truth. The bed and the glow. They do not conflict. They are answers to different questions. And the reason it feels like they should conflict is that we grew up with a picture of space as a fixed stage with fixed coordinates painted on it, and that stage does not exist and never did. There is no floor. There is only what things are doing in relation to one another, which, when you sit with it for a while, is not unsettling. It is quite restful. Because if there is no absolute rest, then you have not failed to reach it. There is nowhere you are supposed to be. Nothing is standing still and doing it correctly while you drift. The idea of being properly stationary, which sounds so much like something worth achieving, turns out to be a description of nothing at all. Everything is moving. Everything always has been. The earth, the sun, the galaxy, the whole enormous local structure, all of it in motion since the beginning and never once at rest, and none of it going anywhere in particular and none of it late. Take a slow breath now, if you are still with me. You are lying somewhere, in a room, and you are perfectly still. And underneath you the ground is turning east at several hundred meters a second, carrying the room and the building and the whole landscape with it, so smoothly that a pendulum is the only way to notice. And that whole turning ball is falling around a star at 30 kilometers a second and has been all your life and will complete another lap by this time next year and set it down almost exactly where it started. And the star is drifting toward Hercules, taking all of us with it and never coming back to this particular patch of space. And all of it together is swinging around the center of a galaxy at 230 kilometers a second on a journey that began when the first dinosaurs were appearing and will not finish for another 200 million years. And while that turn proceeds, the whole solar system is rising slowly through the plane of the galaxy a few kilometers a second on a rhythm so long that the entire history of our species fits into a rounding error of it. And every galaxy you could see tonight, if the sky were dark enough and your eyes were good enough, is streaming with us in the same direction, towards something enormous and away from something empty at 600 kilometers a second, and in every direction around you, passing through the walls and through the bed and through your body at a rate of hundreds of trillions of particles of light every second, is a faint microwave glow that has been traveling since before there were stars, arriving very slightly warmer from the direction of Leo because of the speed at which you are going toward it. You cannot feel any of it. You never will. There is nothing to feel it against, and none of it needs you to do anything. It is not a journey you're taking. It is not a thing to keep up with. It has been running since long before there was anyone to notice, and it will run for a very long time after, and your part in it is only this: to be a small, warm thing, lying still, being carried. Rest now. The room is not moving. Everything else is. Sleep well.